Our speaker today is Ben Wu from Baylor University, and he'll be talking about single top quark production at the Tevatron. Please welcome our speaker. Alex, sorry, do we have a pointer or slide changer?
Right there. There's no slide changer.
Ah, okay. So
there's a keyboard.
We'll have to use this keyboard. This is connected just for
okay.
Yeah.
Oh, okay. Yeah.
But yeah, thank you.
So hello everyone. I'm Zhenbin from Baylor University. I'll talk about the single top core production at the Fermilab Tevatron. So this is the outline of the talk. I will give a very brief introduction about the standard model and top quark, and the Tevatron and the CDF detector. I'll talk about the measurement of single top core production and CDF, which I will focus on because that's what I did. I know most of it. And then also the single top core production and physio. And then I will show you some research for single top core S-channel productions at the Tevatron recently. And then I'll come to the summary. So the standard model, I think we all know that is a very successful theory to describe the electromagnetic strong and weak interactions among all the new subparticles. And we have three types of particles: the fermion, the gauge boson, and the Higgs bosons, which is candidate is discovered by LSC in July 2012. And I think recent studies shows that it's very likely to be a standard model Higgs. So we have the fermion, that's elementary particles, is half spin, and the gauge boson mediate the strong, weak, and electromagnetic force. The top quark, if you old enough in the top group, like I do, usually every top specialist will start with the top quark is special, and then I also hear the complaint for the B physics group say no, all the particles should be special. But it's very hard to ignore this fat boy in the family, right? Because it's so heavy in the standard model that is 38 times larger than the second heaviest quark, the B quark. And because it's so heavy that it actually decays before it hydrogenizes, which means that all the decay product carry the spin information of the top quark that allow us to measure the top property directly. So it became the only Baylor quark that we can measure directly. And also the top sector is expected to be very sensitive to new physics. So the top quarks mainly produced by strong interaction in pairs. So here is the P bar collide each other, and then you have a PT bar productions. And it provides a very rich channel for us to study the top properties, for example, top mass, charge, weight, and cross-section, etc. Also, you can measure the top decay branching ratios, and maybe search for real decay like top decay to S or W, etc. And we also have very interesting forward-backward symmetry. I'm sure we have expert in the room. So that's a very rich channel for the top property we can measure. We study its intensity at the Tevatron. Also, we know that LHC is the top factory, and there's many top physics is being doing at the LHC. So besides these TT bar productions, we have the single top core productions, which is produced via the electroweak interactions. So there's three production modes: the S channel, T channel, and the associated WT channel. So here is the cross-section according to this archive paper, assuming the top mass is 172.5 GeV. And if you sum this up, actually it's half of the top pair productions. I used to complain about that it's only half, but then I realized that it's really fascinating factor that your electroweak production is almost half of the strong productions. And if you're looking for any other physics models, the scale should be about 10, I would say. Well, actually, this is a very surprising factor for us. However, it's still a challenging experiment because if you're going to extract a relatively small signal from a very large background because of the event signature and with a large uncertainty. So then why we're interested in the single top productions? Most importantly, it allows us to direct measurement of this CK matrix element, VTB. So the CK matrices have a very important role within the standard model.
another question. So when you do the single top, is it like a top class anything? So that anything could be missing as well, right? So in your
No, we usually consider have an additional jets.
so always do additional jets.
Yeah, you always need additional jet to be associated with the top production. Otherwise, you can conserve.
Can you study top and bottom?
Yeah, that's the thing. No, I was also wondering, like you, why not top plus missing energy? So, but here probably that's not your motivation.
No.
Well, it's been done. There have been searches for that, but that's not,
Yeah.
I mean, this is really about looking for the
So
standard model
for
process.
Tevatron, you have like
Oh,
top
yeah.
plus missing
Oh,
energy.
yeah. It's just it's a search where this is really about.
This
looking
is
at-
very standard model.
Standard model.
Yeah.
No, also in standard model, like a one jet could be missing, right? Like you produced a T plus B, I understand, but that jet could be missing. And then,
Yeah, it could be. For example, for the T channel, you can miss a jet, and then but we still have the selection to pick up those events. But if, like for example, for the S channel, that it miss a B, then this is not really in this study.
A lot of the acceptance comes from the case where the lepton is missing.
later, but not the B jet is.
Yeah. Right.
It's easier to miss a lepton than a jet, generally in the detector.
How about the T and the Z if the Z is missing energy?
Which one?
For the third diagram, you could have the
Yeah,
top
yeah.
and a Z, that Z goes to new bar, and that would
Yeah.
be missing energy.
Yeah.
Yeah, but it's very small procession in detection.
So he wrote WT, but the use point is you can write
You could make it, so you could make a charm and then a Z and a T. Yeah, that's
Z
just
and T. And
I know, but then you've got you're pulling a B out of the proton there.
Yeah, yeah.
Right, so you'd have to be
Yeah,
pulling
yeah.
a charm out of the proton plus another 10 GeV. So yeah, it's there, but it's very small. Right, we don't see the associated.
Yeah, actually I will talk about
Sorry, this is his
association.
talk.
So, okay. So important thing is that the weekend measured element have to be measured by experiments. And then the direct measurement of VTV is very important for these metrics. And also, the measurement of VTV is a solid test of the standard model because we ask ourselves the question is that is it the CKM metrics have to be 3 by 3, right? I mean, is there any fourth generation exist? And so if you really measure the VTV, at least you can give us some hint about whether or not the fourth generation can exist. Also, you can test the unitarity of the CKM matrix. So the single top Quark was first observed by CDF and D0 simultaneously in 2009. So so far we're at more than 100 citations, and in that analysis, for CDF we have 4 analyses in lepton plus jet channel with 3.2 inverse phantom bomb and 1 missing infant plus jet with 2.1 inverse phantom bomb data. And D0 have 3 analyses in lepton plus jet channel with 2.3 inverse phantom bomb. And then we really go through lots of effort to finally cram the observation of the single top Quark. So the Tevatron, for those don't know, is a proton-anti-proton collider, and the central mass of energy is 1.96 TeV. So we have 2 detectors, the CDF and D0, located in the B0 and D0 points. And it was shut down on September 2011, deliver about 12 inverse phantom bomb data. So the CDF detector located here with the B0 point is a multi-purpose experiment detector. So we have proton, anti-proton collide in the center of the detector. You have a silicon checking to provide very precise checking, which is very important for the B tagging we're going to talk about later. And then you have this open drift chamber, the checker, the COT. And then you have a solenoid outside of the COT, and then you have the electromagnetic and hadronic calorimeter. And at the outer side, you have this muon chamber. So how does the particle looks like in the detector? For example, we can have a jet, which is lots of things where checks energy in the electron and hadronic parameters will cluster into jets. You have muons that go through the detector and have a check in the muon chamber, which we identify as a muons. Electrons have a checks and energy in the electromagnetic parameter. And photon, you don't see a check, but just energy in the EM parameter. So the collision happens every 396 nanoseconds, producing a tremendous amount of data. So CDF actually explored this 3-layer trigger system that just try to recall those events that we think is physics interesting data. So we have the first layer is a level 1 trigger, which is a hardware trigger. And the level 2 is a hardware and software half-half trigger system. And then all the when those events pass these 2 layers of system, we store in the buffer, and then later on have this level 3 form that output to the storage area. So for Baylor CDF group, we was responsible for this extremely fast checker system in the level 1, which is a pattern recognition hardware that try to have this tracking link together very quickly. And then all the data is collected from this trigger system and stored in the event for later process. So for this analysis I'm going to talk about is the single auto production in the lepton partition channel, where you consider only one isolated lepton. It could be electron muons with PT about 20 GeV, like here. And you have a large missing ED from the neutrino. We have the missing ED about 25 GeV. And the event signature you're looking at it have 2 or 3 jets with ET about 20 GeV and eta within 2.8. So the eta is a pseudo rapidity we use a lot in the collider physics because it's longitudinal Lorentz boost invariance. So because you don't know the z position about the collision happen, so using this variable you can really invariance among these collisions. So here is the mapping between eta to the real degree. So you can see that 2.8 we're really looking for the jets that vary forward in the very forward region. And because we know that the top will have a B jet in the final state, so we require at least one of the jets should be detected. So now on slide 13, sorry, I forgot to mention the slides. Slide 13, this is a lepton category we're using. So you can see these eta 5 distributions for the, here is the electrons. So the red one is CEM, the central electrons. And the 4 region, we call it Phoenix HX, is 4 electrons. And the right-hand plot actually is a muon, so you can see we have this dark green area is the CMUP, is where we consider the muon for here is well reconstructed because the muon coverage is very good in this region. Also the CMX is a very well coverage region. So we combine this 4 lepton category as a tile lepton category, where we consider they have very high efficiency for these lepton applications. However, we have other many small category because, and then we don't consider very good because the coverage. For this analysis, we add this iso trap, which is high PT well isolated traps. So you can see from this diagram, it actually covers up this area that where the muon chambers cannot be well instrumented. So by adding this iso trap, we expect about 15% gain just by for this EMC category.
What's the trigger for that again?
Sorry?
What's the trigger for your isotrack?
The trigger is, the iso trap mainly comes from this missing ET trigger. So most we only consider this loose lepton category from the missing ET trigger.
You actually require the isotrack to be pointing to one of the fiducial of the muon detector or not?
You could, I mean, you basically can overlap, right? So if for example, for this, let's pick the BMU, for example, you do have a track pointing to the to that area, and then you can prioritize like whether or not you select it as a BMU or ISO track. So because BMU have a tighter criteria to become a BMU. So once you select it as a BMU, then you can look in the event to see whether or not it's really a good ISO track. Then we'll add it as ISO track. So slide 14. So the energetic partons that come from collisions will fragment and then hadronize into a bunch of hadrons in your detector that go in the same directions. So then in hydrogen physics, we reconstruct this using the Jacob algorithm with the energy cluster in the calorimeters. And the CDF will explore the jet size 0.4. And then for all the jet corrected, we have the corrections to correct the non-uniform detector response, the multiple interaction and the underlying event, etc. Slide 15. So we haven't talked about neutrino yet, because neutrino, you travel through the detector material without any interaction with the detector. However, it will appear as a large missing energy in the system. And then if you consider the transverse plan of the detector should be momentum conserved, then what you did is that you can sum up the transverse momentum of the events, and then you can estimate the missing energy in this transverse plan and call it as a PT of the missing ET. And because in our study is that we assume we're looking, the neutrino should come from the missing ET should come from the neutrino from the WDK. So that means you can fit the missing ET with the lepton to the Wmax. From there, you can actually constrain the PZ component of this neutrino. So that gives you some handle about this PZ component of the neutrino, where you can use it for later reconstruction for different variables. So the B quark, slide 16. So a B quark for collisions will immediately hadronize into a B hadrons. And the B hadron will have a long lifetime, so you won't. So you will travel through a small distance and then decays. So which means that in the event you're going to see is that a displaced secondary vertex. So what you can do is that we explore different kinematics, and then we have this ZVT algorithm that try to tap these secondary vertex jets. And so far, the beta efficiency is one of the limiting factors of our event acceptance. Also, there's a probability that you could mistake a jet, where it's by looking at the secondary vertex, this LXY, if it's in the opposite direction. So your secondary vertex is here, and when the other jets go to these directions, then you know this should be a mistake. So from here, you can have a better estimate about your mistake probability for the B-tagging. So slide 17. So in hydrogen physics, our study mostly rely on the comparison between the collected data and the theoretical predictions. So we simulate events according to this standard model theoretical predictions using these Monte Carlo methods. We're using match element generator to produce parton level informations, and then these parton are showered by this parton showering program producing hadron level informations. And then you simulate these hadron interact with the detector by we have this special CDF simulation package. So here is the table for different processes we consider in this analysis, and for the match element generator and the parton shower program. So I will talk about the single model using the power hat for the single top, also the QCD modeling. So slide 18. So there's a challenge for us to model the situational productions Because originally, if you draw the Feynman diagram, the tree level, you could have this we call 2-to-2 process. A quark and bottom produce a teacher node top and a Q bar. And then later on, if you pass the Proton shower, PCR will do these backward calculations. That because you knew because the B quark from the proton is so small, so the majority of the B quark should come from gluon splitting. So in that case, the PCR will do these backward calculations that produce another secondary B quark, and this B quark should be very soft. So also because of this initial initial state, we call it 5-flavor calculations. And then there's if you consider this the gluon splitting into your tree level calculations, which will make it a 2 to 3 process. And because you're calculating the gluon splitting in the tree level, this B quark should be much harder than from the PCR backward calculations. So because of the initial state, you only have this 4-flavor quark, so we also call this 4-flavor calculations. So in the past, what we did at CDF is that we using that graph to simulate these two processes. And then we try to do this mixture manually, just try to make sure that it match to the theoretical positions, where we're using the Z-top positions, which are theoretical calculations. So what we did is that by matching these two samples, to make sure that the secondary B quark PT spectrum is smooth, and then the composition of these two processes, according to Z-top position, should be 16.7% within this CDF acceptance, which means that your B-jet PT about 20 GeV and eta within 2.8. And in 2009, the Campbell, the MCFM actually calculated this directly using this 4-flavor calculation. And from his prediction that he saw that is splitting this 4-flavor production should be about 30.8%, which is much larger. So it tells us that we're expecting much harder secondary B jets from the events. I apologize for the graphic resolution, because this is kind of a private problem requested. So
which are you using? Are you using the MCFM?
no, yeah, this is MCFM.
So that's his calculation.
Yeah.
Is
So,
MCFM.
yeah,
So what are
MCFM.
you, remind me what you're using? You're using the POW head?
Yes, that brings me to the next slide.
Okay. Sorry.
Slide 19. Yes. So to overcome this problem, I implemented this power head within CDF. So it's a next to linear calculation, as we know. And then we made this comparison between power head, the standard means this Megrad mist, and the MCFM 4-flavor calculations. So on the top is the pattern level information without any acceptance. And the bottom is that after this CDF acceptance cut. So here you can see that there's a slight mismatch in this region, but once you apply the acceptance, they show a very good agreement for all. So we think using PowerHead, we can have a much better modeling for the teacher node. That's why we switched to PowerHead.
The top right is, you see the black is quite a bit away. And what are those peaks? Like you have
So the black is, you have these two processes you try to mix. But when you fine tune it in after the acceptance, then in the before any acceptance selections, you can have this kind of weird feature. So basically, this should be the 2 to 2, and this 2 should be the 2 to 3 process.
2 to 3 is a little bit
It
highly eta.
Yeah.
I see. Because those are how B jets kind of a little bit boosted.
Yeah.
I see. So that's why you see these two peaks, and then the central is the.
Yeah, that's right. Okay.
Did you, sorry, for the XCF sorry, sample. How did you process the detection relation using CFC?
No, here is only parton level information. You just like the tree level output.
So there's no detection simulation?
No even hydronizations. So you don't have that. So SEFN just give you theoretical distributions.
Oh, so this is parton level. That's why you have kept the B definition in all the way up to eta equals to 4.
Yeah.
and all that.
Only this are only parton. Yeah.
How do you get the other B from, so this one is from, you mentioned that it's just that it takes the B from the BDL, so that means BDL will generate another B from the initial state.
Yeah.
And you're saying that B is, generally speaking, softer
Yeah.
than it would be in a parton level calculation. So, so if this is at parton level, so this one is not for the PTO, right? It's for PTO, it's not a parton level calculation. I just don't miss the point.
Oh, I see. So yeah, so this I think this B you need to pass through a PCR to do this.
Oh yeah, the question is, do you have that B in the plot?
You mean in this plot?
Yeah.
Yeah. Yeah, I think you have to. Otherwise, you don't have these particular B jets. So from this diagram, you only have one B.
That means the slide on the plot on that slide is not parallel level, but it's actually.
Yeah, I think there's a. I didn't really do this, but I think you can do some setting that you only do this secondary B jet calculations, but not do the shower. You can just tune the PCR parameter car to do something like this.
All right.
Okay, then the WT channel. So we knew that the single-dot core can be produced with the associated with W bosons. It's a very small cross-section of Tevatrons. And to model this process, we have this well-known problem of interference effects with the TT bar. That basically means that you have the WT process, and then because again you have initial gluon split into BB bar. Then when the mass of this W and B reach to the top max, then your calculation will interfere with the TT bar process. So that's an issue about how do you really simulate this. So with Powhead, there's a two approach that are available within the Powhead. One is called a diagram removal, that is just like you consider the top core as a not detectable particle. Or you can have this diagram subtraction by adding an additional term into your Lagrangian. You will remove this continuation from the TT bar. But doing this, you allow you to keep the top cores of final state particles. So we look into this, and for example, here's the mass reconstruction using a WB. You can see that there's a foreign spectrum, and then you can see this continuity. Because the red ones come from diagram subtraction, so you basically cross this continuity around the top max region. And what we did, and if you apply CDF acceptance, you can see this. Actually, these two modeling agree with each other very well. So what we did is that we're using the combine of these two modeling as WT channel simulations, and all the differences assume as a systematic uncertainty.
That's Monte Carlo on the right? Or is
This
that
one?
data?
Yeah.
That's not data, that's,
So yeah, this.
so that's if you put in the red and the black, which is a pure parton level, you get the same answer, is what you're saying.
Yeah.
Which means that your data can't tell the difference between the red and the black.
Yeah, that's right. Because
Which is pretty different looking, but okay.
once somehow your selection can actually remove of this area.
No, it's not sensitive to it. Remove it.
Yeah.
If you can't tell the difference, then it means it's not sensitive.
Yeah, we cannot tell the difference of these two. So okay, that's slide 22. Now I talk about this QCD modeling. So the QCD process can actually mimic this lepton plus jet final state. For example, glue to 4 jets, and one of the jets you can misidentify as a leptons, and you lost identify one of the jets, which mimic these final states. Or you can gluon split to BB bar, where the lepton and neutrino actually come from the B. So, but it's almost impossible for us to simulate the QCD process because the QCD have a huge cross-section, and there's a huge number of Feynman diagrams when you need to consider, but the selection efficiency is very, very small because it's very unlikely for this to happen in our detector, but because of huge cross-section, it still became one of the big background for us. So at the end, we're using this QCD enriched data, try to model the QCD multi-jet event. So for the TLC, this high lepton category, we're using this anti-electron model. So you ask for the event that if don't pass all your electron ID, you fail some of the electron ID cuts, then you know this electron, in this region, the data mostly should be QCD enriched. So you can use those data to model our QCD. And for the EMC, the loose muon category, we're using the non-isotic muon, like inverting the isolation requirement, then you can really get a region that have a QCD-rich samples.
Ken, how many slides do you have? I
I
want to hear the answer, but
about
there's a
half.
3 o'clock semester colloquium that many of us have to go to.
Okay, I'll try to speed this up.
4 o'clock. 4.
Oh, is it 4?
Yeah. Unless you want to give it a look.
You can give
I
a,
don't think anybody would want to listen to me today, but is it 4?
Yeah.
I
Not as
have,
long as you want, what do I know?
okay, I have
What do
that.
I- 3 o'clock.
Yeah. So we have the background veto, we veto dilepton, and veto Z, and veto cosmic ray. And also, I would say the QCD is a big issue for us because we even try to model it, but you have a large uncertainty, so the best thing to do is just cut away the QCD process. So we have this it's called single-top QCD veto, which is a set of cuts to remove this QCD enriched region. So here is the 2D diagram between the mass significant with the W transverse mass. So this plot is from the Monte Carlo process. So you have this region, mass looking region. And also you can compare with the pre-TET data, where you have 2 peaks here. Once you do the subtraction, you can see there's a peak around this region. So we knew this should be QCD process mostly. So you can adjust your cut to remove this region. Okay, then to know, it's essential for us to predict the contribution for different background because if you want to do the measurement precisely. So for those well understood process, for example, TT bar diboson and Z-pass jets, we normalize them to the standard model cross-section. But for W-pass jet and QCD, we don't have a fully handle of these two processes. So we normalize it to data in the miscigenity spectrum like this. So for example, here you know your data have this kind of distributions, and your QCD tend to have a low miscigenity when the W-pass jet have a high miscigenity. So by allowing these two temperature to free flow, actually you can try to normalize the contribution from these two processes. And furthermore, for the W-pass jet, we separate out into W-pass light flavor and W-pass heavy flavor. And for our other study, it shows that the W-pass heavy flavor actually need to have additional scale, try to match the data, which we call a K-factor scale. And for us to model the light flavor jets, we actually calculate it using the mistake probability in our signal region. So slide 25. So this is the final event EL table for our W-pass jet large equal to 1 B-TEC jets. So here you can see that if you take to some mass, you can see the signal over background is only 0.06. And our signal is almost half of the background uncertainty from this table. So that means it's very difficult for us just to do a cut-based analysis like LHC did without sacrificing your signal EL. So we're using a multi-variable technique just try to have a better signal background separations. So we explore this neural network technique, which is a 3-layer feed-forward neural network. And basically each input to different layer applied with a weight. And then the node between different layers is connected with the CMO function, looks like this. So any adjustment on the x-axis will have a very large effect on the y-axis. And then you train a neural network to have the output as 1 for the signal and -1 as the background. The training process is just try to minimize the difference between the neural network output to the true information you have. Then by iteratively adjusting this weight as the input until this minimization is reached. So for this analysis, we actually train the neural network using 11 to 14 different variables. So this table here, in all this A category, we separate out into 2 or 3 jets with 1 or 2 BTAC and TLC or EMC. So we're A channel separately trained. And to really optimize for the analysis, we train the S channel into 2 jet 2 tag category because you have this B jet is a very enriched S channel in this category. And the rest of category we train for T channel only. So it's a combine, and then we combine them as a measurement. And because one thing we're trying to do is that because we try to have a very precise measurement of the single top, and we try a new method is that you train the neural network. Usually you train the neural network using this nominal events. But we try to mix with this systematic sample, which means the event, adding the event that have some sort of systematic varieties into the training. So that you try to have is that a neural network that give you good signal background separation, but it's not very sensitive to certain large systematic varieties. So we saw about 3% improvement by just doing this simple criteria. So here I'm going to show you these 4 very powerful discriminant variables we use in the analysis. One is called the jet flavor separator. So it's that for the beta jets, you can really train a neural net to separate out the heavy flavor from the light flavor using different kinematics. So here from this plot, you can see that the W plus heavy flavor have a peak around this region, when your W plus light flavor actually have a peak on the negative region. And actually, this region is mostly charm enriched region, actually. So there's another analysis actually using this to study charm. And the bottom is the reconstructed top mass, because you can see from here that we have a well reconstructed single top and TD bar is around the top mass region. All the other background actually have a much lower top mass reconstructed region. So on slide 29 is an MJJ, which I think is very, very famous variables. And you can see that the MJJ gives you pretty good separation from the top process to the background, especially the diboson peak here. And on the bottom plot is the Q eta, which is another very interesting variable for the single top. So for T channel, your B jet, which comes from the gluon, so is from the C quark mostly, and your quark, because we have proton-proton collision, so we have 2 up, 1 down. So you're going to expect 2 valence quark in the initial state. So that means from the PDF, you knew that this 2 quark will be a much larger energy than this initial B quark. So that will cause your light flavored quark have the preference to go around these valence quark directions, which gives you pretty forward jets. So that's one of the reasons we really need to look into the forward jet for just because it include this P channel. And because of charge conservation, actually, if you're looking for a lepton charge, it's correlated with the top charge. So then if you multiply the lepton charge with a Q, you can always, from this case, you know that you will go to the forward region, the positive region, with the proton. So charge. So if you consider antiproton, to the opposite, -1 times -1 equal to positive. So again, you go to this region. So that's why in here, you can see there's a very different asymmetry distribution just from the single top. like this, and where all the background is symmetry distribution. So then this one tech region. However, in our zero tech, which we try to validate our modeling, we saw this discrepancy in this another region, the other side of the detector. So this is something we really try to understand, but unfortunately we cannot figure out. So we consider this as a systematic uncertainty on our analysis.
So you also see the peak on larger. Okay, so that one because of this argument, but on the lower side you are saying why it's coming. Right?
This one?
Yeah.
Oh no, here because it's zero tech, so it's really it's not our. So the dragon is a little bit confusing. So here you can see this red area is our signal, but in the zero tech you don't really see our signal because it's the background dominant area.
But on the right hand side, like around q times theta equals to 2, you see a peak.
Yeah. So yeah, I spent lots of time on this.
So not only on the negative side, but also on the positive side, there are 2 peaks, right?
Yes. Yeah. So this could come from several things. One thing I will investigate is that whether or not, because we're using algorithm for the simulations. So the question is whether or not the background simulation is correctly done in this region. So we compare with different generators, but I don't see a large difference.
You also see that peak.
Yeah. So this is kind of a mystery for us. We're trying to figure out what's in this area.
What Monte Carlo are you? So that's dominated by W plus heavy flavor, W plus light flavor.
Yeah.
Overwhelmingly light flavor.
Yes, it's a zero tech region.
And so that has so that's W plus jet, so that's got a very large asymmetry. And what you're seeing is that the data has less asymmetry than the Monte Carlo.
Yeah. So actually, maybe this is CDF talk, but if you go to, I did several talk about this, try to understand this feature. Well, I said I didn't come to any end.
That's
So-
interesting that you have a asymmetry like that.
Yeah. So actually, there's
How many jets again do you have in this thing?
So
This is lepton plus 2 jets?
lepton plus 2 jet, yeah.
2 and only
zero
2?
tech.
2 and only 2 or 2 or more?
2 jet only. This is probably 2 jet only. But if you include 2 or more, it's still the same because 2 jet are very dominated in Tevatron. So the prop won't change much.
Well, they become very top dominated.
Yeah.
2 and only 2 with 0 tags.
So actually, that's another study which I want to do, but I really didn't do because of this. Is that if you can try to measure the single top and single anti-top, right? If you assume a well CV conservation, you expect the cross-section between them should be identical. But there's several papers out there describing that it could be different from the new physics contribution.
Does Hal have the same problem?
No, how do the trick is count on the 2? So once you count on the central region, everything is fine.
Larger data.
So
He just cuts.
yeah, because his jet selections, for S channel, you only need central jets. The whole reason we're looking for the forward jets is because of the T channel.
Wait, this is eta of the lepton jet?
It's a light jet.
Oh, the light jet.
Sorry.
So this is the Q of the lepton times the eta of the light jet.
Yeah.
So charge multiplied.
Yeah,
by
okay.
this. So, but you're saying that you have used these models with kind of CPS symmetry. So did you explain? Okay, you
I try.
I try. So
I
what happened?
try. But the problem is because of this, then you have a huge problem when you try to measure it. Because this is a trump. The trump of the lepton is here in your input. Then you cannot do you cannot measure the trump of anything because the model is here. So, which is quite a pity thing because I'm really trying to get this done. Okay, so slide 31. But the good thing is that our neural turned out to be pretty good. So here you can see the neural network from the single top is really peak on the 1, and all the background is in -1. And one thing I remind you is that we don't really train on the QCD process because we don't really have QCD modeling. But if you input your QCD, you can see still it's all background light.
So what is this discriminant?
The discriminant is a neural network that this is the combine of all the neural network. Yeah, so this is just show some interesting variables. And now we cross-check our neural network in the zero-type region. It looks pretty good. And this is the output from our signal region. So you can see the data lies with the petitions. And also for this analysis, we consider lots of systematic, and still one of our dominant systematic is the scale energy scale, because pretty big problems. And I won't go through the detail of this, run out of time. So then comes to the cross-section measurement. We're using the Bayesian approach, and then you took all the uncertainty to the Newton parameters. And and then calculate using Bayesian approach. This is the posterior from the you calculate it from the likelihood fit, and you extract the maximum as your cross-section, the 68% as your uncertainty, by assuming the top mass is 172.5 GeV. And when you input, you do make the assumption that these 3 channels should have the standard model ratio among them. And from here, we extracted the single cross-section to 3.04.
How sensitive is that to the uncertainty on the top?
The uncertainty on top?
I would guess not very, but
on top mass?
On top mass, right? Because we just measured the top mass to a much better precision.
It's
you know, with the recent combinations, and it's closer to 173-ish.
Okay. It's not on top 5, I would say, but I forgot the order. Okay, then you also can extract this VTB value, because we mentioned that the single top is proportional to VTB squared. So you can directly measure the VTB doing the similar fit, but you consider more systematic uncertainty. For example, the top mass dependent cross-section. Here you make no assumption about top mass. But assuming the VTB much larger than the other 2 and have a CP conserving vertex, you set the limit about VTB about 0.78 at 95% confidence level, and we check the VTB about 0.92. And then you try to remove this standard model assumption between the ratio between different channels by allowing the input temperature to free flow in the fit. And here we can see we have the S channel cross-section and the T and WT channel cross-section. Here, because the WT is very similar to the T channel final state, so we kind of combine them together. And what we studied shows that this WT is really negligible in this fit at the end, because the contribution is very, very small, and we're really not sensitive to that signature. And from here, you can see that this box is the standard model predictions. Our data prefer most S channel and less T channel comparing to the standard model. And from here, we also can extract the cross-section separately for different channels. And again, when this is assumed standard model predictions, and you can make a comparison that is really our data have some sort of preference in this study. And the WT channel is very negligible. And slide 36. So I'll show you the result from the D0 using 9.7 inverse Vanderbilt in the lepton subject analysis. So for example, the single model they're using is called single top. Is some fine-tuned single top simulation within the D0. And they're using the 3 analysis using boost decision tree, the Bayesian neural network, and this neural evolution neural network. And these 3 analyses about 75% correlations, and then they combine all these 3 analyses using a final Bayesian neural network, just trying to get the best of it. the analysis. And they train all these multivariable techniques separately for S channel and T channel. So then here is the plots showing the data and versus the predictions. You can see that they are pretty good agreement, and for T channel, it really lines up quite well. So for their slide 38, for their cross-section measurement, here consider they really don't take into account for WT channel, even though it's small, but we took into account because we try to measure the single top cross-section in general. And here they neglect this one. And they're also using the Bayesian approach for the cross-section measurement. And they have a slightly different methods to make this measurement without the assumption of this S channel, T channel ratio, which is quite fancy paper. I really don't fully understand how they did this. But what they measure is that they measure 4.11 picobar of single top cross-sections. And then similarly do this 2D fit for S channel and T channel. One interesting thing is that the standard model for this area is around here. They measure a similar S channel cross-section, but they have a higher T channel cross-section. So you remember the previous several slides, what we measure is that our point is around here. So CDF perform more S channel than T channel. So this is some sort of interesting feature.
Can you go back 3.34, go back to yours?
Mine?
So is that a prediction? What's the prediction? What's your expected?
Oh, here we don't really show the prediction. The prediction is very close to the measurement.
All right, then go to the next one. Yeah, no, back.
This one?
Yeah. So they predict 3.34. Yeah, so you've got the same thing. So you've got 3.1, so you've got basically 3.37.
Which one are you talking about?
I'm just adding the 3 standard model predictions.
Oh, okay, yeah.
Because I was surprised by the 3.34 and I realized that it's... So, all right, so the predictions are the same. Basically, the predictions are the same, it's just the answers are very different.
Yeah,
the overlaps, the oval overlaps are not.
Okay, slide 39. Around time. So because they train the neural network separately for S and T channel, so they can actually do the measurement alone for the T and S channel. So here is the T channel cross-section similarly, and then they actually claimed the first observation in 2011. And for S channel, they measure 1.1 picobar of S channel, but they only have 3.7 standard deviation. So obviously they need help from our CDF side. So slide 40. So we have this, recently have this S channel analysis using the lepton plus jet category also. And this analysis really optimized the selection for single top S channel by just like using the central jet to end up within 2 instead of 2.8. And also, because the similar final event signature from the S channel is the WH, the Higgs associated with W boson such. So we kind of inherited most of the information from that analysis. And one of the biggest inheritance we have is this Hobbit tagger. So the Higgs optimized B-jet identified tagger, which is a neural network just try to really explore all the kinematic we can have. And you can see this neural network output that the signal is really peaked on this region, and the background is really separate out. So by cutting a different neural network output, we define a tagger and use detect tagger. So also we have another neural network which we call the B-jet selector, because you have 2 B-jet in the event. So this neural network will try to select the best B-jets that originated from the top. So you allow for better top reconstruction. And we have a final neural network discriminant to separate out the signal from the background. So slide 41. So here's the top mask reconstructed using the this B-jet selector. As you can see in the pre-tap, the control region, the modeling pretty well. And then you can see in the signal region, they're all peak around the top mask region window. And the bottom is the output from the final discriminant. You can see you can have actually you can see closely is that the signal is peaked from this region, and this is no signal here. So slide 42. So we come to the cross-section measurement. We measure the astronomical cross-section at 1.41. And we run the pseudo experiments on many pseudo experiments for different hypotheses. The only background hypothesis and the background plus signal hypothesis. And then we observe a values graph here, which correspond to 3.8 standard deviation, which becomes the evidence. So also, we have this astronaut search in the missing ET plus jet channel, where you have a lepton that is missed in these reconstructions. And so you only have is the B jet and the missing ET, so main plus jet final state. And this analysis actually can recover those electron muon that missed and reconstructed in the lepton plus jets. And also, you can include this W to tau decay, because now the hadronic decay tau will appear as a jet in the event. So it's really complementing channel of the lepton plus jets. And one problem that we have is for the missing ET plus jet analysis that the QCD background is huge. And we train a neural network to separate the QCD from the signal region in this case. So actually there's another neural network. Then in this signal region, there's another neural network to separate the signal from the boson plus jets. And then the last one, there's another neural network to train from the signal from the TD bar process. So it's a 3-layer of neural network in pro in this analysis. So slide 44. So from there, we extract the cross section is about 1.1. But if you you're looking at the uncertainty, we don't get a very strong significance. So the map plus jet analysis combined with the lepton plus jet analysis, and then from here you can see that we saw a 4.2 standard deviation from the S channel alone as CDF. So still, whatever we do, little bit far away from 5 sigma. So we have to do a Tevatron combinations. So here is the combination from Tevatron, from CDF and D0. We basically combine all the discriminant templates, including all the correlations. So here you can see in the log scale, the signal and data point lines up pretty well.
Do you know what kind of structure is it? Structure?
Oh, here is the structure, you mean the log scale?
No, it's kind of drop, then kind of stay, the flattening, then drop. And the minus, say, minus 0.8.
Minus 0.8.
Then it's kind of flat. Flatten distribution. Do you have any kind of step function structure?
No, I don't think you can have any step function structure. I mean, I haven't saw the product, not log scale. So, but I think the reason you put the log scale because you have more sensitivity in these pins. But yeah, I haven't seen the other parts.
It's a funny thing because it's an ordered plot as opposed to the usual kind of plots.
Did you see the normal plots?
The look is fine. I just see kind of.
Yeah, but I mean, I think the log scale makes it more complete.
Maybe TT
No, but it's an ordered plot. I mean, you take all the bins and you order them, then you put them in. So it's a funny thing.
Where you see two distributions in there? Because here it looks like two distributions. Two separate distributions.
TT bar.
Yeah.
Ah, okay. It kind of, the matter jet is completely kind of dropping. The TT bar stay
TT
flat.
bar precisely.
That's why it's the function.
And it's equally distributed.
Yeah, true.
Okay. Okay. And crossing ejection for the H channel is 1.29, and here is the comparison among different studies. You can see they show a good agreement within the standard model predictions. So slide 47. So at the end we extract the combined significance from the Tevatrons. So here you can see. So this is a background-only hypothesis, and this signal plus backgrounds, and the data shows at this point, which correspond to 6.3 standard deviations, which is observation of the single top H channel. So slide 48. So the summary of current single top Quark, which is from Christina. So the result is based on the up to Memorial 2014. So the observation, we have the S plus T, the T, and the S channel recently from the Tevatron combinations. And just a couple of months ago, the WT associated channel actually is observed by the CMS analysis. So that means all these single top potential modes have been observed. And the precision measurement, the Tevatron still have the best single top measurements. And the T channel so far has come from the D0, and the combined S channel measurement have about 90% uncertainty. From the LC, they have a very precise T channel already because they have lots of gain of the T channel cross sections. But it's still very difficult for them to do the S channel. And recently, the WT channel about 23% uncertainty. So then come to the summary that I'm presenting the most recent single top analysis at Tevatrons. And the observation of this single top H channel is a great legacy from the Tevatrons. And with this recent observation of the WT channel, all the single top potential nodes observed. And now we come to the era of precise measurement of the single top Quark at LHC. Thank you very much for your attention, and for further information, you go to our page.
So, questions?
When are you going to get all of these papers out?
Soon, very soon.
Today, tax day. That's right.
Yeah, the test day, yeah. So tomorrow is the single top day.
Through this combination of 3 MVAs for the D0 analysis, is it clear how much they gain over just using one, or the best of the 3?
They have 75% correlation, so it means that you really still get a little bit from each one, so around 20 something.
Squeezing.
Yeah, I think we did that for the observation also, like 4.
How do they handle overtraining? Or, I mean, presumably the same signal data sets being trained, right?
So first, overtraining is really, each analysis you need to check the overtraining issue. And so yeah, when you do this combine, you really need to take account, compare different signal data, we call, the more different analysis, and then you have some sort of a weighted input to the final neural net, which event is considered the most important event. So they have some sort of, I don't really have detail about what they did actually on the D0 side, but that's my impression from the last time we did at the CDF.
Can you say more about overtraining and what's bad about overtraining and why it should be avoided?
So overtraining means that if you train a neural network, for example, I use neural network, is that you input the signal and background. You tell neural network this is signal, this is background, right? If you train so well, the neural network it should only remember that the second event should be signal, the third event should be background. It's not like really exploding the kinematic, but it just remember like this, the ordering of events, for example. And the way for you to test whether or not you overtrain is just to apply the same neural network to another almost identical data set to see whether or not you get identical performance. This is one way to test whether or not you overtrain.
Sounds like overtrain is not a really good name for that.
Right?
Well, this plot on here, it looked at, well, I think what happens is that they split the data set into two regions, and you train on one half, and then you test on the other half. So you're not selecting events and then kind of reselecting them with something designed to select those signals.
You want a neural network to perform identical.
All right, so it's selecting on particularities of that sample rather than the parent distribution that is presumably drawn from.
Yeah. So
So it will say, oh, I can get 70% rejection on this sample, but if I give it another equivalent sample drawn from the parent, it might only give 50%. And you define that as being overtrained.
Yeah, that's good.
So that's your definition of overtrained.
Yeah. So you don't want your neural network to perform two different, two similar data sets. Otherwise, you know you have the
All
problem.
right, I can see that worry. I don't know that I would call it overtrained, but okay. Yeah, it's not bias training. It's a systematic uncertainty in the efficiency in its ability to do what it says it did. It's a name. I don't. That's just a fun name.
Okay, any more questions? If not, then let's, oh, sorry, did you have another one? Okay, let's thank our speaker again.
Very nice.